So the challenge of this lab is to determine what the relationships are between color, wavelength, absorbance, and concentration. Okay? So you're going to need to know these relationships in order to measure the absorption of light by a colored solution to determine the concentration of the absorbing species in that solution. So we're going to be using concentration and relating it to the concept of absorption. Okay? So let's get a little bit of background. The color of a solution is an important tool used by scientists to gain information about the composition of the solution. Color is a physical property that is useful for both qualitative and now quantitative analysis. A qualitative method yields information about the nature or type of a compound in a solution in a sample, whereas a quantitative method provides numerical data for the amount of a compound in a sample. Spectroscopy is the study of the interaction of light and matter. A spectrophotometer is an instrument that uses electromagnetic radiation from a selected region of the electromagnetic spectrum, such as UV, visible in this case what we're going to use, or infrared, to analyze the absorption or transmission, we're going to be looking at absorption of radiation by a sample. The basic function of a spectrophotometer is shown in figure 1. All right, and we'll look at that in 1 second. The electromagnetic spectrum is the entire range of possible wavelengths or frequencies of electromagnetic radiation. In this investigation, a visible spectrophotometer will be used. It scans the visible region of electromagnetic spectrum from 380 nanometers to 750 nanometers. Typical light sources for visible spectrophotometers include xenon and tungsten lamps. So let's look at this. So what's going to happen is the spectrophotometer emits energy, and it passes it through whatever you are studying, whatever solution you are studying, and it is going to be able to measure the absorption, okay? What we're going to use are glass cuvettes, okay, and they're going to be used as sample cells for visible spectrophotometers. The desired wavelength is focused onto the sample, okay, to detect any absorption or emission of light. So we're going to be studying absorption of light, just as I explained using that diagram above. Spectrophotometry is an analytical procedure that uses electromagnetic radiation to measure the concentration of a substance. The success of a spectrophotomic technique requires that the absorption of light by the substance being analyzed must be distinct or different from that of other chemical species in solution. The wavelength that corresponds with the highest absorbance without exceeding an absorbance of 1, which we'll look at in just 1 second, we don't want it to be above 1, is the wavelength that should be used. And I'll explain all of that and how to use a wavelength using the spectrophotometer. Note, once the wavelength is chosen and set on the spectrophotometer, it is not changed nor used in any calculations. We're going to set it on the spectrophotometer and then we're going to leave it alone. All right, so here's some context. Spectrophotometry is an extremely important tool used in forensic science to determine the detailed chemical composition of evidence obtained from a crime scene. It can be used to determine the concentration of either a single chemical species in solution or even the concentration of a species within a mixture of species in solution. For example, it can be used to determine the mass percent of copper in brass shell casings collected by a crime scene investigator, and then match the brass composition to a particular manufacturer. So our ultimate goal in this laboratory is to determine the percent composition of copper in brass, and that can eventually be used if we had, for example, a CSI situation. So here are your pre-lab questions. Number 1, using the graph below, what wavelength should we set the spectrophotometer to? So we want the maximum absorbance, but it has to be less than 1. So if you look at this graph, the peak is already less than 1, so figure out what that wavelength is where you have that peak, and that's what we're going to set our spectrophotometer to at the very beginning of the lab, and then we won't change it. What we're going to be using in this lab extensively is called Beer's Law. Now, Beer's Law is A equals ABC, so what I want you to do is I want you to research online each of these variables and then identify them below. Then, if this is the equation we're using, what do you think your x variable will be and what do you think your y variable will be? So I'm not going to be giving you what each of them represents, but capital A, that's going to be your y, and the lowercase c, that's going to be your x. So you got to figure out what those represent. All right, number 3. So I actually gave you a Beer's Law problem. So it says, based upon the Beer's Law plot shown in figure 2 for the absorbance of copper sulfate versus concentration, what mass of copper could be produced by a complete reaction of excess zinc metal with 50 mils of copper sulfate that is a measured absorbance of 0.685. Now, you're going to solve this problem, and I'm not going to help you, but one of the reasons why I wanted to talk about this really quickly was because that helps you to show the relationship between absorbance and concentration. In this problem, since I've already created this graph, which is going to be the first thing that we're going to do in this lab is actually plot different concentrations versus absorbances and create a graph that looks just like this. Since you know the absorbance is 0.685, you then can figure out the concentration, and then it's going to be a normal stoichiometry problem. So I just wanted to show you that relationship. So here's the laboratory procedure. Step 1, you're going to determine the mass of the brass shell casing, and then you're going to put it into a small beaker. So let me show you what that looks like.
So the first thing we're going to do is we're going to weigh your shell casing. Okay, so you're going to find the mass of it, all right? And using that mass, you need to determine the volume of nitric acid that you need to add in order for all of it to react. So you're going to follow the instructions that I'm going to explain in just 1 second.
You're going to assume that your brass sample is 100% copper, and you're going to calculate the minimum volume of nitric acid. It's 15.8 molar nitric acid that would be needed to react completely with the brass. So just as a hint, before you solve this, you need to make sure that you write a proper net ionic reaction in order to do the stoichiometry for this. Then under the fume hood, I'm going to take a little bit more than 2 mils, more than what you anticipated in number 2 based on your calculation, and I'm going to add that to your shell casing. Okay, and we're going to leave that. I'm going to explain really quickly what we're going to do afterwards, but at this point, we're going to leave it, and then we're going to move on to actually creating your Beer's Law curve. So after the metal dissolves completely, okay, add 50 mils of distilled water to the beaker. Again, I'm going to do this. Then you're going to remove the beaker and transfer the solution to a 100 ml volumetric flask. You're going to rinse the beaker 3 to 4 times with 5 mils of distilled water, and then you're going to add it all to the flask. Dilute to a volume of 100 mils. Okay, the excess nitric acid will dissolve the zinc and copper metal in the brass. All right, so this is what you're going to do after we've created the Beer's Law curve, after you've given the nitric acid the opportunity to dissolve away your shell casing. Now, the reason why I didn't show this, I want this to be a surprise. I want you guys to see what it looks like. So you just have to follow the instructions, and it's pretty simple. All right, step 5. In order to create a Beer's Law curve, you need to create a graph of concentration versus absorbance. Now, you already saw that in the pre-lab question. You saw what that graph's going to look like. Now, you're going to create one yourself. You will therefore find the absorbance of 5 different solutions with all of those different concentrations, respectively. Beginning with 0.400 molar solution, determine how much water in stock solution you must mix in order to create 8 mils of each solution. Have me check your calculations before you make the solutions. So, for example, I'm going to do the 0.200 molar solution. You're going to be using the formula, the dilution formula, M1V1 equals M2V2. M1 and V1 are going to be your concentrated solutions. M2 and V2 are going to be your dilute solutions. Okay? So, here's my calculation. M1 is my concentrated solution, my stock. I have a 0.400 molar solution. I want to know what volume of it I need to add in order to get a dilute solution, so that's going to be my V1. I know that the final concentration is going to be 0.200, and I know that the final volume is going to be 8 mils, right? I want a final volume for all of these of 8 mils. So what that tells me is that the volume of stock solution I'm going to add is going to be 4 mils. So I'm going to add 4 mils of my stock solution in order to get a final volume of 8 mils. That means I need 4 mils as well of water. So 4 mils of water, 4 mils of stock solution. So you're going to do this calculation now to create a 0.100 instead of 0.200 molar solution, then a 0.05, and then a 0.025. All right, and then have me check your work.
So in this lab, we're going to be making a copper solution using our brass shell casing. And that's going to be blue in color, and using our spectrophotometer, which I'll show you in 1 second, what we'll be able to do is determine the concentration of copper in the solution by finding absorbance. But in order to do that, we need to create a Beer's Law curve. And so that's going to compare concentration and absorbance, and we will actually create that curve. Well, in order to do that, we need 5 different solutions with different concentrations. So we have one solution already. It's 0.4 molar copper nitrate, and now we need to create the other 4 solutions. So I'm going to show you how I created the 0.2 molar solution. So you're going to get a total of 6 cuvettes. Okay, so these are glass be careful with them because they can break. Now, I'm going to fill one of them with water, and then the other 5 are going to have solution. Well, I can add the 0.4 molar solution really easily and not have to do any calculations or any work. So what I'm going to show you is creating the 0.2 molar solution. So since I want 8 mils of solution, I'm going to take, and you should have gotten this from your calculations, 4 mils of my copper nitrate, and then I'm going to take 4 mils of water. Now, what I normally do is I fill all of the cuvettes with the proper amount of water for each of them, and then I fill them with copper nitrate because that prevents you from actually contaminating any of your substances. So I need 4 mils of water. So this is a volumetric pipette. Notice, and I don't think you can see this, but they're little numbers and then they're larger numbers. You're going to be using the little numbers to actually measure. There's a scroll right here where you can scroll up and scroll down. So what you'll do is submerge the pipette into your water and you'll scroll up until you hit 4 milliliters. Okay, so I'm at 4 milliliters right now. I'll put my water down. I'm going to put it over the opening of my cuvette, and then I'm going to hit this button right here, which allows me to release. I can also just push this button here, and that will also release it. So I'm going to push the button. Okay. Now I've got 4 mils of water in my cuvette. Now I want to measure 4 mils of my copper nitrate as well. So I'm going to take it, same technique. I'm going to make sure this is all the way down so I can pull up the solution. I'm going to scroll up to 4 mils. Okay. And then I'm going to add it to my cuvette. Now, if you are completely sure that it mixed, awesome. But what I always do whenever I'm mixing in a cuvette, I'm going to, again, make sure that you push that down so it's all the way down. I'm going to scroll up. I'm going to suck up some of this liquid. And then I'm going to release it. And that clearly you can see it. You can see it mixing. Okay? So now my solution's mixed. So I've got one of the 4 solutions that I need to dilute. And you're going to do the other 3 calculations. Okay? So what you'll have in front of you is a total of 5 solutions, one with a 0.4 molar and then the other 4 that you created. Once you've created that, then we can go over this to the spectrophotometer and use that to actually measure the absorbance and compare that with concentration.
Before you actually use the spectrophotometer, you are going to set the wavelength, okay, to whatever you decided in your pre-lab, and then you're going to calibrate it with a blank, which is just a cuvette filled with water. Before you actually add a cuvette to a spectrophotometer, you need to make sure to use a Kim wipe in order to clean off the cuvette and make sure that the solution does not splash onto the spectrophotometer. Okay? In the data table below, you're going to record all of the absorbances that you get. So let me show you what you're going to be doing.
So this is the spectrophotometer. So what we're going to do is we first need to zero this. Okay? So the way we're going to zero it is we're going to add a solution of just water. Okay? So for each case, just in case there's water, you're going to take a Kim wipe and you're going to wipe it off. And then you're going to open the spectrophotometer and carefully, don't push too hard, push the sample in. Okay? So if you notice, it's not at 0 right now, so I'm going to hit 0 for it to 0. Okay, now I can use the sample. So I'm going to pull this one out. Now I'm going to put one of my samples. You're going to do a total of 5 of these. Okay, and so I get an absorbance, which is what I'm going to measure, of 0.02. Now, one thing that I didn't mention, before you use your spectrophotometer at all, one of the instructions in your pre-lab was to determine the proper wavelength. So if you notice right here, this says wavelength, you can adjust to the correct wavelength, whatever you decide. Once you adjust it at the very beginning, before I did anything, any of what I just did, you need to have that set and then you're gonna leave it alone. You're not gonna use that anymore, all right?
Once you've measured all of the different absorbances for the different concentrations, then you're going to use the absorbance and concentration values, and you're going to create a graph in which absorbance is your y-axis and concentration is your x-axis. Okay? You're going to create a best fit line using Excel, and then you're going to calculate the slope and the y-intercept for Beer's plot. All right, now that you have your plot, right, now that you know the relationship between absorbance and concentration, what you can do is, using the spectrophotometer and the equation above, you can determine the concentration of your unknown brass solution. Specifically, you can simply take the solution that we created from your shell casing, You can pour a little bit of that into your cuvette, and you can measure the absorbance using the spectrophotometer. Once you know the absorbance, you can use your Beer's plot in order to figure out the concentration, and that way you'll know your concentration of copper in your solution. From that information, from your concentration that you figure out using Beer's plot, then you need to determine the mass of copper that dissolved in the solution. Then you need to calculate the mass percent of copper in the brass, which you can totally do. And then you're going to research online what a typical mass percent of copper looks like, right? How much copper is typically in brass shell casings. Once you find an accepted value, then you're going to find the percent error.